Welcome, everybody, to our second MathWorks mini-series. Here at RoboNation. We're very excited to have Abhishek Shankar join us from MathWorks, and he's going to be talking about control algorithm design using Simulink. Throughout the webinar, you are free to put up any questions that you have in the chat, and we'll go ahead and answer those at the end of our call. Or throughout, depending on how Abhishek wants to answer some of those questions. So yeah, it'll be over the course of the next hour. He's going to be talking about all things to do with Simulink there. But feel free to scan the QR link or follow in our chat. You can join our Discord to continue this conversation after this particular webinar. But again, thank you so much for joining us. We're super excited to have you here. And again, feel free to ask any of those questions in our chat here on YouTube. So I will go ahead and turn it over to Abhishek to give us all the cool and exciting information.
Thank you, Alicia. Let me start by sharing my screen. All right. Welcome, everyone, to the webinar. Thank you for joining us today. I'm Abhishek Shankar. I'm going to be talking about how you can design control systems in Simulink and deploy it as ROS nodes. So let me just give you a brief overview of what I'll be talking about today. I'll give you a brief introduction of control systems, and we'll talk a bit about system dynamics, which is really important when you're trying to design a closed loop controller. And then the first algorithm that we'll be talking about is the nonlinear model predictive control, nonlinear MPC. And then we'll talk about pure pursuit, which is also another famous controller for trajectory tracking. And then we'll talk a little bit about the MathWorks award that we are very excited to start from this year. And that will be the conclusion of the webinar. So to get started, we all know control system is pretty crucial to your robot, whether if you want to follow a reference trajectory or any reference that you want to track. So for example, if you have a battery management system for your robot, you want to make sure that the state of charge is within a particular level. So you might have to optimize your performance to make sure your battery level stays same. Or you could also do trajectory planning or trajectory tracking. If you have a ground robot or a surface robot, you do it in 2D, 2 dimensions. And if you have a drone or a underwater vehicle, you're going to do that in 3 dimensions. For this example, I'm going to be using a differential drive robot, which has 2 wheels that are being controlled by separate motors. This is a simple example, and to move forward, you just spin both the wheels forward, and to move left or right, you change the wheel speed. So just running the right motor makes your robot turn left, and vice versa to turn right. So we'll be using this as an example to design our control systems. And we'll also be talking about the system dynamics, which is, again, as I mentioned before, very important when you're trying to do closed loop system design. So before we go into the control systems, we'll start about the dynamics of our differential drive robot. We'll begin with the state vector, which is all the information that you would need for your application. So in this webinar, I'm going to be talking about reference tracking or trajectory tracking. So the parameters that I would need for that purpose is just the position, X and Y, and the theta or the heading, or how the robot is oriented with respect to your map. So that is going to be my state vector. It's going to have 3 variables, X, Y, and theta. And then we're going to get the dynamics, or how these state variables change with respect to time given a particular input. So the input to our system is going to be linear velocity V, and then angular velocity omega or W. So again, state dynamics is just the rate of change of these variables with respect to time. So the dot on top represents, says that it is the rate of change. And you can see that X dot is, with some simple trigonometry, you can see that X dot, the rate at which the X variable changes, is V times cosine of theta. And how Y changes is V times sine of theta. And theta is going to change depending on your angular velocity, which is omega or W. So that is your state vector and your system dynamics. And we'll now go to our first MPC, first control algorithm, which is a nonlinear MPC. So in a lot of aspects, this is similar to your regular MPC or regular model predictive controller. It calculates a bunch of control actions over a control period, and it uses future state predictions and a constrained optimization to ensure that you provide optimal control inputs to closely track the trajectory. The main difference here is that the prediction model used can be nonlinear. In other MPC models, like the regular MPC or adaptive MPC, you need to have a linear model or a linearized version of your model. But this nonlinear MPC, as the name suggests, can take a nonlinear prediction model or nonlinear state model. And in our case, a state model is nonlinear. If you remember, we had the cosine and sine terms, which are nonlinear terms. So we're going to be using the nonlinear MPC to showcase how you can use this to control your differential drive robot. In MATLAB, you use the NL MPC object to define a nonlinear MPC object. And this requires the state function, which we defined earlier, which is basically how x changes with x, y, and theta changes with respect to time. And then it optionally needs a Jacobian function. I mean, this is optional, but best practice is to provide a Jacobian if it's available. And in most cases, if you can model the dynamics of the system, you can kind of get the analytical Jacobian. If not, MATLAB would calculate the Jacobian in the backend, but this makes it slower. And nonlinear MPC is kind of slower when you compare it to the linear MPC or adaptive MPC. So it's good to make it as fast as you can by providing a Jacobian function. And I'm going to be talking about nonlinear MPC particularly today because we have actually done a video on adaptive MPC with RoboNation last year. If you go ahead to RoboNation's YouTube channel and check out their MathWorks series from last year, you'll see that a team used adaptive MPC for their submarine, which was pretty well done and greatly explained by the university for the RoboSub competition. And we also have a bunch of videos on MPC. You can always go to our MathWorks YouTube channel and just search for MPC. You'll see a whole playlist by my colleague Melda, who explains in detail about MPC design. So, like I said, nonlinear MPC requires a state function that we've already seen, and then the Jacobian. So the Jacobian is the derivative of your dynamics of the system, or x dot, with respect to the states and the control inputs. So you're going to have two matrices. A is going to be your derivative with respect to the states. This is how it is defined. You're going to find the derivative of x dot, y dot, and theta dot with respect to your states, x, y, and theta. And if you remember the dynamics from before, your x dot does not depend on x or y, it just depends on theta. So you just differentiate with respect to theta. So these are partial derivatives. And with respect to x and y, you're going to have zeros. And then with respect to theta, it's going to be minus b times sine of theta. And similarly, your rate of change of y dot with respect to theta is b times cosine of theta. And all the other partial derivatives are going to be zeros. And the next matrix that we want is the derivative with respect to the inputs. The inputs to the system here are the linear and the angular velocity. And the B matrix looks like this. It's the derivative of x dot, y dot, theta dot with respect to linear velocity v and angular velocity w or omega. So again, you can refer back to the system dynamics. This will be your Jacobian with respect to the inputs. And once you have all of this defined, let's go switch to MATLAB and see how you can model this in Simulink. So I'm going to open my live script. So first, we'll start by defining our state function. We know that the number of states is going to be 3, x, y, and theta. And our control input u contains linear velocity as the first element and angular velocity as the second element. And theta is the third element in the state vector. So x start, as we had defined before in the PowerPoint, x start of 1 is going to be v times cosine of theta. The first element is going to be v times cosine of theta. Y dot is going to be v times sine of theta. And your theta dot is just going to be your angular velocity. And now we'll define the Jacobian. Here you've taken the inputs again, a state and the inputs. The number of states is 3, the number of inputs is 2, and your linear velocity is the first element of your input, and your theta is the third element. And again, just as it was shown in the PowerPoint, it's going to be zeros everywhere, and then the third column is going to be negative v sine theta, positive v cos theta, and 0 for the A matrix. So I am just going to change that. I'm going to define a matrix of zeros, and then just change the third column to the values that we saw before. And similarly, you set the values for your B matrix, which is the derivative with respect to the inputs, linear and angular velocity. So once you have these two defined, you can then create the NLMPC object. So here I have the number of states 3. The output, the NY, is also 3 because we are predicting what will be the next X, Y, theta position, the next position at the time step. And then you're also going to get the number of inputs, which is 2, which is your linear and angular velocity. So once you have these three, you create the NLMPC object by passing all of these. And then you're going to set a bunch of parameters. The sample time is 0.1 in this case. You can set it to whatever sample time that you want your controller to run. I'm going to use 0.1 here. And I'm going to use the prediction horizon of 20 sample times and the control horizon of 10 sample times. These are parameters that you use to tune your controller. So we recommend that you start with a value and then see how your controller performs, and then to adjust it accordingly based on the performance of the controller. So if you want it to meet the reference faster, you kind of change these values. But you're free to play around and see how it works in simulation before you deploy it to your robot. And then you have the state functions defined. So the state functions are what I had defined here. I'm passing these state functions. And it's also a continuous time model, so I'm going to set that to true. And we're going to also set weights. So the MPC optimization requires weights for the output and the manipulated variables. So for the output variables, I'm going to set a positive value for X and Y and 0 for theta. And this is because I don't really care how the robot is oriented as long as it goes to the reference X and Y position. So that is going to be my output variable weight. But if you also want the robot to track the heading properly, you can set this to a positive value. So if you set this to 0.5, again, it prioritizes these two over this. But if you set this to 0, it's not going to look at that closely. But if you set this to equal weight as the X and Y, then it'll try to match all three of them equally. And we're going to set some weights to the manipulated variables, which are your linear and angular velocity, and the rate at which these manipulated variables can change. And then we're also going to set some constraints. We don't want the manipulated variables to be too big or too small. So we're going to give the minimum of -2 meters per second for the linear velocity and a maximum of 2 meters per second. And similarly, for the angular velocity, you set the minimum and the maximum value that it can apply. So again, this depends on your robot and your system. So if you want higher values, you can just change these constraints. And once you have the constraints and the weights and the model defined, you're going to have to validate it. So for validation, you simply use a initial value of X and U, which is your state and your input vector. I'm going to set all of these to 0 and then use the function validate function, which will tell me that the state function looks okay, the Jacobian function looks okay. No output function is specified. So this actually means that I'm not taking into consideration any of the external disturbances. So if you have, let's say, a boat on the sea or on a river, your output is not just depending on your inputs, but it also depends on the waves or the current in the river, which might push it left or right. So you can model those external disturbances too, in which case y will not be equal to x, it will be x plus those disturbances. But I'm taking a more ideal scenario here just to show you how to design the controller. But if you have a system where you know that they're going to be external disturbances, you can always model them. We have some resources for that, but you can also reach out to us if you're having trouble with modeling these disturbances. So once you're done, you're going to get these parameters for simulation. So I'm going to run this section to define the object, and then we're going to open the Simulink models to see how we can see this in simulation. All right. So this is my Simulink model. There are three main blocks that I have here. The controller is the main part, which has, let me zoom in a little bit. Controller is the main part, which is the nonlinear MPC that we define. And then we have a plant model, which is a differential drive kinematics model that comes with Simulink. It basically does the same thing as the state vector. Like uh, if you give it the linear and the angular velocity, it tells you how the state changes in the next step. And then you have the observation, which is basically a bunch of scope or graphing tools to see how your state is tracking the reference state. So for this example, I've given a reference of 6, 6, and pi by 3. And then you feed that as a reference to the nonlinear MPC. So we are asking the robot to go to 6, 6, pi by 3, which is x, y, and theta. And you're going to give the feedback from your model into the controller. And then you're also going to feed the last manipulated variable. So at time step 1, you want the manipulated variable that was given at time step 0. So you're just going to have to store the previous value in the memory and then feed it into the nonlinear MPC. So if you open the MPC, you're going to have to define the controller. And this was, again, what we had defined earlier in our live script, which should be in our workspace. So you can see that it was defined here. I'm just using the same controller here. And once that is done, you can then run the model. I'm going to run the model. I'm just running it for 10 seconds to see how it performs. So once it's done, you can open the scope to see how closely it's tracking the reference. So you can see that, zoom this a little bit. You can see that the yellow line is the reference that we want to track, and then the blue line is the robot's actual X position. So it's able to meet the reference in about 5 seconds or 4.5 seconds, which is pretty good. But if you want to make it faster, you can always adjust the constraints on the inputs or the prediction horizon or the control horizon to make sure that it reaches faster. Or if in this case we don't have any overshoot, but if there is overshoot, you can also tune it. So I'm going to close the scope, and again, you can see how it is in Y. What we just saw was the X reference. Y is also being tracked pretty well, and we'll see theta. And you see that theta is not exactly matching. And if you recollect, we set the weight of theta to be 0. So it's not going to pay a lot of attention or pay a lot of weightage for the tracking of your heading, but it still does a decently good job of tracking the reference value. All right, so now that we know that it works and you're okay with how it is tuned and with the controller's performance, you can go ahead and deploy it as a ROS node. Let me close this model, and I have another model that is similar to the one we have, but it's gonna subscribe to ROS topics, so you can deploy it as a ROS node. So in this model, it's the same thing. The nonlinear MPC has the same MPC object defined here, but you're going to have a subscriber and a publisher. The subscriber is going to subscribe to your uh, position or the state variable. So I'm using the post from TurtleBot simulation, um, and then I'm just taking the XY theta from the simulator and sending it as a state variable. So if you open the subscriber, you get a chance to configure your network addresses. So before I go into that, let me open my virtual system to start ROS and start the simulation as well. So I am gonna go ahead and start ROS. I'm using ROS1 for this example. I'm using ROS melodic to be exact, but you can do the same thing with ROS2 as well. I'll tell you what changes that you need to do for ROS2 in just a minute. So I have my ROS master running at this IP, and then I'm going to go back. Let me start the Stutterbot simulation as well. ROS run. Okay. So I have the simple Stutterbot simulator. I wanted to be kind on my virtual machine today. I'm not going to use the full Gazebo server, but if you're using the full Gazebo server for the Stutterbot simulation, you just have to replace the topics that you're subscribing. I believe the Gazebo server publishes ODOM instead of post, and you publish command well instead of, I think it's turtle command well in this case. But it's just the topics that would change. The rest of the workflow is similar. So let me go back to the Simulink model. I'm going to open the subscriber here, and then you can configure network addresses, which would be the port at which the IP address at which your ROS master is running, and then the port defaults to 11311. In most cases, this doesn't change. And then your host name will be your PC, the PC that's running MATLAB, that IP address. So once you have that, you're gonna subscribe to this topic. You can always select topics from the ROS from your ROS machine. So these are the ones that are being published. I chose Turtle Post. And then I'm gonna show you the same thing in the command well. So I have a geometry twist message, which is what you use for your command velocity. And you're going to take the linear and the angular velocity from your controller and feed it into the linear x and angular z. And you're going to send that as a total one command velocity. So again, this is very similar to the model that I used before, but instead of a plant model here, I'm using the simulation. So I'm not doing, I'm not modeling the, excuse me, I'm not modeling the system. I'm rather using a simulation to get the feedback of where our robot is at a particular time. All right. So now that you have the system defined, you go into modeling and select model settings. So I have configured this before, but I'm just showing you how you would do it if you want to change it, if you want to generate ROS node out of it. So you're going to go to hardware implementation here, and you're going to choose ROS. You also have ROS2 if you're doing ROS2. And then for me, the vendor is going to be generic 32-bit, but if you're using a target hardware like a Jetson Nano, you will have to choose the ARM compatible because that's an ARM-based processor. And that's pretty much it. You just have to choose your system properly so that it's configured for the code generation. And then you can close this part, and that would open the ROS tab. Open that, and then you click on remote device. So if you click on manage remote device, It shows you the IP address of your device, your username and password, so it can SSH into that device. And then I'm using Melodic, so my ROS folder is going to be op ROS Melodic, and this is the location of my Kraken workspace. So once you have this defined, you can test the connection. So what it will do is basically ping that device and then see if you have all the user privilege, um, and also check if your Catkin and your ROS workspace are defined properly. And once all of them is done, it says everything is successful and it's going to disconnect. So you're able to establish a connection with your remote machine. And once that is done, you can go ahead and choose build and run. So this is going to build your uh, code as a ROS node and then deploy it to your virtual machine. I am going to click on that. So code generation typically takes a few minutes. So it's going to have to generate the code and then SSH into your machine and transfer that code and then do Catkin build or Catkin make on your machine. So the whole process takes a few minutes. But in this time, if you have any questions, do drop it in the chat and I will get back to you um, while we wait for the code generation.
Yeah, we have two questions in the chat right now.
Sure.
One of the questions is, does MPC provide auto designing?
Sorry, does MPC provide?
Auto designing?
So we don't have the designer app for nonlinear MPC, but if you have a regular MPC, we do provide a design option where you can choose your manipulative variables and your state model and all of them in a GUI, so it makes it easier to design. That feature is not currently available for adaptive and nonlinear MPC.
And then our second question is a little bit more in terms of if one of our students is able to get in contact with you, but they've been
Sure.
having a problem getting a response for their LQR regulator. So they were wondering if they could have an email contact to be able
Oh,
to.
yeah, sure. You can always email to RoboticsArena@MathWorks.com. I also show that link at the end of the slide. You can send out an email to that, and we usually get back within a day or two. And we also have experts in optimal control. So if it's some kind of a tricky problem to solve, we'll get you in touch with our controls expert, and they will help you getting your LQR working.
Perfect. Well, thank you. Those are our questions right now. So
Okay.
let's keep going.
Awesome. Yeah, feel free to ask any questions. And I'm still waiting for this to get done. Let me go back to the simulation. Okay, so code generation is still happening. So it's now building. So it's done generating the code. It's starting to build the code in the target device. Yeah, this is probably the slowest part of this whole process. But once it is built, it should run it automatically in your target device, and you should see a turtle bot move to the particular reference position that you have specified. All right, so now it's connecting to ROS. That is your typical Catkin build, which I can make. I'm not really sure what it's using right now. Once close to completion, we'll switch to the simulator to see how it's performing. Actually, let me also echo the post topic so you can see what the values changed. Yeah. See, my virtual machine is pretty slow. You can see why I didn't open the full gazebo server. That would have taken forever. All right, so we're currently at 5.5. I think the reference is 2,2. Okay, so it's done. It's building. It's 87% done. So once it's 100% and it starts deploying, you'll switch to the simulator to see how the robot moves. So I think it's done. Let's switch back. Oh yeah, you can see shuttle bar moving to closer to 2, but you can see that it is oscillating a little bit. So this can be avoided if you have like a goal threshold to minimize these oscillations. But again, these are things that you can do to tune your controller better. So again, in your state space model, it's going to be different compared to the simulation, but it is kind of how you go about designing your controller. You start with something, you see how it performs. If it's not to your liking, you can always go ahead and change some parameters to tune your controller and then deploy it again. So it's more of an iterative process, but you can see that it's kind of converging to that 2-2 value. So now I'm going to stop this simulation. Actually, hold on. Let me run this again. Where go back to the folder. So I'm going to my Catkin source folder, and you can see that the differential drive in LMPC ROS was created here. It has all the ROS nodes here. So what you would do is, if you want to now run it again, you just do ROS run. So ROS run, I think it's differential drive. Oh, okay, so I have differential drive and then MPC. And then I'm going to run that node. And once it's run, it's going to do the same thing. It's going to go to 2-2 and it's still oscillating. So, but if that's how you would run the system once it has already generated, and if you want to now, you can close MATLAB and do most of your work in your ROS system. So you use MATLAB to design your controller, tune it, and then once you're satisfied with it, you deploy the node and you can stop MATLAB at the background. So let me go back to our presentation. Oh wait, let me hold on and close this model. Save it. And now I'll go back to my presentation. So that is how you would go about designing a nonlinear MPC. And now I'm going to go to the next controller, which is Pure Pursuit. This is a pretty famous controller developed by Carnegie Mellon in 1990. I believe they used it to win the DARPA challenge at the time. So it's a pretty cool algorithm. It assumes a constant linear velocity. So linear velocity is fixed and it's just going to change your angular velocity to track that reference. So you can set it to any linear velocity you want, but the controller only is going to output your angular velocity. The main parameter that you use is the look ahead distance. It determines how much you look ahead to plan your control inputs. And there is one limitation for this controller is that it does not stabilize the robot at a point. So once you reach the goal distance, you need some kind of a threshold to make sure that it stops. So you usually do like a distance threshold, find the distance between the goal and your current robot. And if it's below a particular threshold, you tell the robot to stop. So that again is something that you can tune depending on how close you want it to the goal location. So let me go back to our live script. I'll open the Pure Pursuit model. Right. So again, the overall structure is kind of similar. You have a subscriber that subscribes to your state, which is your pose, and you have let me zoom in a little bit. You have waypoints or goal points that you want it to go. Again, for this example, I'm using a constant block to input the waypoints. But in your case, you might be getting the waypoints from your planning algorithm. So if you're using the uh, the nav package from ROS, you can use that to plan your path and then just subscribe to those waypoints from Simulink. You can also use our navigation toolbox if you want to plan your path in Simulink and have your workflow all done in Simulink. You can do that as well. Again, there's a lot of flexibility. We are very compatible with other tools. So you can have your nav algorithm running in Python, but do your control in MATLAB and then deploy it as a C++ node. So there's a lot of compatibility advantages when you're using Simulink, and it also makes controller design super easy. And that's probably the reason why a lot of industries use our tools for their control system design. A lot of automotive, aerospace, and defense networks use our tools to design their controllers for complex machines like cars, rockets, and flights on submarines and stuff. So it's really easy. You just again give the uh, reference points and the posts that you subscribe from ROS, and again zooming in, you have a pure pursuit model in Simulink. If you open that, uh, it'll ask for your desired linear velocity. This is the constant velocity that it would be driving the robot at. And then some parameters like what's the maximum angular velocity that you want to set. And this is the parameter that you tune, how much you want to look ahead. So if you're looking too short, then you might miss a couple of waypoints and start oscillating. And if you're looking too far ahead, you might miss a waypoint and completely bypass that to go to the next one. So this is something that you'll have to tune and to see what works best for you. But these are the parameters I have right now. And then, like I said, you need a goal threshold for this controller. This is simply it takes the current position and the goal position, calculates the difference, and sees if it's less than 25 meters. Not 25 meters, sorry, 0.25 meters. And if it is, that's the threshold that I've set. If it is less than that, it's going to stop the simulation and not publish any velocity commands. So I'm going to take these velocity commands. Okay, in this subsystem, we are just multiplying it by our at goal function. So if it says it is at goal, then this value is going to be 0, and both your linear and angular velocity will be 0. If not, this will be at 1. So this is a Boolean, and then it will just multiply your velocity by 1. So it's just send the same velocity again. And then I have the same publisher here as a geometry twist message. We're going to set the linear velocity to linear x, and then angular velocity to angular c. So once this is done, you do the same thing. You go to modeling, model settings, and make sure you set the coder to ROS or ROS2, whichever one that you're using. In your hardware implementation, you'll have to choose ROS and also your device vendor based on if it's a PC or if it's a Jetson board or some of the other target boards. You just choose those. We do provide a bunch of options. So there's a good chance that whatever you're using, there'll be a way to input that into Simulink. So once that is done, again, go back to ROS. You're going to check that you can still access the remote device, test it. Again, it looks like all the test turns out positive. We are able to connect to the device. And once that is done, you can go ahead and do the same thing, which is build and run, which is going to generate code for your pure pursuit model and then run it in ROS. So let me go inside my virtual machine. Okay. I'm just going to restart this so it's back in the original position. And let me go back to Simulink. It's still generating code. Again, if there are any questions, I can take them now. Do let me know if you have questions in the chat.
Yeah, we've got one more.
Oh,
Annie asked, do you need an observer matrix to remove a fuzzy controller block and replace it with an LQR gain?
I'm not really sure about that, about the fuzzy part, but I can take that question and forward it to one of the teams. We'll get back to you. Can you also send that question to RoboticsArena@mathworks.com? That way I can route it to the right person for that question.
Fantastic. And we'll make sure to put that email address in the chat right now for you guys so you guys can reach out directly to
Yeah.
them. Thank you.
And also, if you have like a model for that question, you can send the model over and we can help debug that for you as well. So don't feel shy to reach out. We're always there to help. Especially if you're participating in RoboNation competitions. We love those competitions. We love all the students who are working there. It's really exciting to see all the stuff that you're building, and we would be happy to help you with anything.
And as many of you probably know, Abhishek is a former IGBC competitor, so he understands everything
Yeah,
that you guys are going through as you face these competitions and have all these kinds of questions. So he's the perfect person to ask when things pop up, and he'll make sure to direct you to the right people if he doesn't have that information himself.
yeah, that is right. Thank you, Alicia. So yeah, coming back to the webinar, you can see that the total bar moved uh, to the position that that was specified in the goal. Let me hold on. Let me switch back to Simulink to see what was the goal position that I gave. Okay, so I asked it to go to 7, 8, 8, 9, and 9, 9. And the goal position is 9, 9. So it seems that the robot did reach that position. Let me check this raw topic echo. I'm just gonna print one value just to see where it is right now. So it is at 8.7 and 8.9, which is pretty close to 9.9 because we have set a threshold of 0.25. It's able to reach that, so that is good. I'm gonna close this. For some reason, it's stuck. But so as you can see, it is able to go to that position. But just in case you want to run it again, you open the simulator and you can run your node as you would any other node. Sorry, run. I think it's pure pursuit. So if I run the model again, it should do the same thing. Go to those reference points that I was specified in the Simulink model, and then it should just reach the goal position of 9, 9. But yeah, that is how you would go about designing your controller in Simulink and then deploying it as a ROS node to your ROS machine. Again, you have a lot of controllers. As some of the questions says, there's also LQR, which is one of the other optimal control that's used a lot. There's also a video on our website, RoboticsArena, where you can see a team using LQR for their submarine control. And like I mentioned, with RoboNation, there was another video where we used adaptive MPC for submarine control. And there's also a lot of other controllers. Even in MPC, you have the linear MPC, you have the gain scheduled MPC, and you have the regular PID, which works in a lot of cases. but PID is a little bit more tricky to tune when you have multiple thrusters or multiple motors to control. You'll have to have individual PIDs for each of them. But this is how you would go about designing your controllers and deploying it in ROS. So I'm going to go back to my presentation. So we saw, just to summarize, we saw how to do nonlinear MPC and also pure pursuit. And then I'm going to talk a little bit about our MathWorks award. We are excited to announce a new award for the robotics competition. That is one of the biggest competition held by RoboNation. If you have not heard of it, you should totally go check it out. It's a great competition and gives you a lot of valuable experience that is useful not only for your academics but also at the industry level. And the award is worth $2,000. The MathWorks Design Award basically just rewards whoever is using our tools creatively for their robot design. And the $2,000 split among the top 3 winners of the award. And I'm sure RoboNation would probably send more details, but Alicia can explain any details that's going to come out for the robotics competition.
Absolutely. We're going to be sharing some more details directly with our RobotX teams, as well as over the next couple of RobotX team times, we'll be sharing some more information as well. So we look forward to getting you guys all excited and having all the details so that you're able to apply for this particular award and get recognized for all the work you're doing with your MathWorks designs.
Yeah, it's a great opportunity to also learn new software, new ways to design your controllers or other algorithms, and using a tool that's actually used in the industry a lot. So it gives you valuable experience. But that is all I have today. Again, if you have any questions, please reach out to RoboticsArena at mathworks.com as shown here. We usually get back within a day or two. I remember one person asking about LQR. Please reach out, send us your questions, any supporting files that you have, so we can help debug that for you. And if you're also looking into getting started with robotics, or if you're a new team that is going to participate in any of the RoboNation competitions, feel free to reach out to us with any questions you have with robot design, and we can help you as best as we can.
Thank you so much, Abhishek, for joining us today. We're really excited to continue this conversation with our students. Our next session will be in June, so we'll be hosting that on June 13th. We really look forward to having all of you guys there. We'll continue to share that information with you guys, and we'll send out an email with this link so you're able to share it with all your friends and your fellow students that have any questions about these aspects of MathWorks and everything that Abhishek's been able to speak about today. So thank you again. Again, please feel free to email RoboticsArena@mathworks.com with any questions regarding MathWorks. And if you have any other specific questions about RoboNation or any of our competitions, feel free to reach out to humans@robonation.org or autonomy@robonation.org. We look forward to hearing from you and seeing you at our next session. Thank you.
Thank you.